Hi all, this is 8.1 integration by part, or for short, a lot of people just call it IBP, or some people just call it by part. Right? There are many different way of saying this method, but they always mean the same thing, which is integration by part, and that's what we're going to focus on today. Now, before we get into the actual integration by part, I want to show you how we derived this method, right? So let me do a quick review on product rule, right? So if you're taking the derivative of a product of two functions, let's say f of x and g of x, and this is equal to f prime multiplied by g of x plus f of x times g prime of x. Okay. Now on the left hand side, what we have here is derivative of f times g, right? So we can read this as like f times g prime, right? The whole thing prime is equal to f prime times g plus f times g prime. Okay. Now, in order to get back to the original functions, which is fg, we have to take the derivative of this thing. Now, take the integral of the left-hand side, right? So if we take the integral of fg prime dx, that is equal to the integral of f prime times g plus the integral, forgot the x here, plus the integral of f times g prime dx. Now on the left hand side, by the fundamental theorem of calculus, this is just equal to fg, right? And of course, there are some constant if it's an indefinite integral, but let's worry about that later, right? So fg, and then it's equal to this thing, right? F prime g dx plus f times g prime dx. All right. Now, what I'm going to do is I'm going to move one of them to the other side. Right. So I'm going to move the first one to the left-hand side, and on the right-hand side, we only have integral of f times g prime dx. Right. And on the left-hand side here, which I'm going to write down on the right-hand side, is fg minus the integral of f prime times g dx. Okay, and that is essentially how you get integration by part from product rule. Now, there's nothing. All this work is just to show you how we get the result for integration by part, the method. But later I'm going to give you a more thorough walkthrough on how to use integration by part and when it can be used. Just like everything in mathematics, we have opposites, right? Opposite operations, opposite numbers. And here, integration by parts can be thought of as the opposite of product rule, right? Derivative is the opposite of integration and vice versa. So here, integration by parts, that's some sort of integration, and that's the opposite of product rule, which is some sort of a type of derivative. All right, so let's move on. Okay, so this is what we had from our last page. And to make this a little easier to work with, we're going to introduce u and v. So function f is going to be u, and then g is going to be v. So this was kind of like substitution. So I'm going to let u be f and v be g. So du will just be f prime dx, and dv will be g prime dx. Then we can rewrite the whole thing as integral of u dv is equal to uv minus v du. Okay, so that's it. This whole thing is the key of integration by parts, IVP. Now, I'm going to show you a really easy way to memorize this formula. Now, integration by parts is one of the shorter formula that it's nice if you can memorize it. So there you go. So UDV, that means you don't vote. Right? UDV is equal to you vote minus VDU, vote, don't you? Okay, and that is a very nice way of memorizing the integration by part. I learned this way to memorize since I was in high school, and now I still remember it. So you can see how well this method works. Right? UDV, you don't vote, is equal to UV, you vote, minus VDU, vote, don't you? Right. So the one thing you need to remember is this is a minus here. Right. It's always minus in integration by parts. All right. So give you an idea on how to use this. So usually we'll be given the integral on the left hand side, right? Some integral is in this form. And essentially what we're doing is we're trading this integral for another integral to work with, okay? And sometimes too, why do we need this? The reason that why we need this is we want to get a simpler integral than the original one. Okay, that's the goal. We want to get a simpler integral than the original. All right, now there are kind of like two techniques that we're going to use. So first, we want to choose u to be a function that becomes simpler when differentiated, right? If a function, for example, like ln, right, ln is a little hard to work with, but if you differentiate it, you get 1 over x, which is pretty easy to work with, right? And second, you want to make sure that dv can be integrated. Right. Now, this will make a lot more sense when we look at our first example, but just keep this in mind. Choose u that so it's simpler when differentiated, and make sure that dv can be integrated. Okay, so first, this is a technique on how to choose u. So we have these 5 types of function, L for log, I for inverse trig, A for algebraic functions, T for trig, and E for exponential functions. So we're gonna go in this order, right, from top down, right? So within an integral, the function, the type of function that you see first on this list is going to be your u, right? So for example, if I have an integral of x squared times ln x, all right? So let's look at the first one. Does it have a log function? Yes, we have a log function. Then we're going to do substitution and let u be equal to ln x, right? And the other is going to be your dv, right? So dv is going to be x squared and the dx. Don't forget the dx. Okay, so that's basically how you set up your integration by parts, right? So log function, natural log, right? The basic log with some base, standard log, right? And the inverse trig function, all of the arc one, so arc sine, arc cosine, and all the fun stuff, right? Algebraic function like polynomials, and polynomials and quotients, right? Fractions, all those type of stuff. Rational functions, square roots, radicals, right? And trig functions, sine, cosine, tangent, so on. exponential functions, right? E to the x, some number to the x, and so on. Okay, so we have everything we need, and let's just dive into a bunch of examples together. All right, our first example, we're going to integrate x squared times e to the 5x dx. All right, so to follow our last page earlier, last page of notes, we're going to follow this order to pick out our u. All right, so let's see. First, L for log. Do we have any log? No. All right, let's move on to the next one. I for inverse trig. We don't have any inverse trig. A for algebraic. And yes, we have an algebraic function right here, right? The x squared. That means we're going to let u be x squared. And the rest is going to be dv, right? So dv is going to be this part right here, e to the 5x times dx. Okay. Now, I'm going to write out an integration by part formula on the right here, right? So remember, u don't vote is equal to u vote minus vote, don't you? Right. So looking at this formula on the left-hand side, u dv, we already have u dv, and next we need to figure out what v is and what du is. All right, so let's just do this. So du is going to be the integration of this, the derivative of this, which is 2x dx, and we're going to integrate dv to get v, right? So integrate this thing, right, which is the integral of e to the 5x dx, and that's going to be e to the 5x over 5, right? And here we're not going to worry about the plus c yet. We'll just add the plus c at the end. Okay. All right. So from this point on, we have everything we need. We know that integral of u dv is equal to this thing. That means we can rewrite this integral as the right hand side, right? So u, that's x squared times v, that's x squared e to the 5x over 5 minus v du, right? So v is this thing, e to the 5x over 5 multiplied by du, which is 2x dx. All right, so I'm gonna clean this up a little bit. X squared e to the 5x over 5 minus integral of 2/5 x e to the 5x dx. Okay, now we just need to worry about this integral, but notice that this integral also contains two types of function. We have a first degree monomial right here, and then an exponential right here. Right. So in this case, this is when we have to evaluate, use integration by parts again. And notice that we still have an algebraic expression, which is just a first degree monomial, and then another exponential. So we're going to do the same thing again. Okay. So we're going to let u be 2/5 x, and dv be e to the 5x dx. Right? And then it's the same process over again. This is our new u dv. All right, so du is 2/5 dx, and then we have to integrate this. So v is again e to the 5x over 5. Okay. And then let's go ahead and rewrite this. So the first thing, x squared e to the 5x over 5 minus, I'm going to move on to the next one, minus, put everything in a big bracket. All right, so this thing, I'm going to apply integration by parts again. All right, so this whole thing right here is your new integral of u dv, right? So that's equal to uv minus integral v du. So uv right here, that is 2x e to the 5x over 25 minus the integral of v du, which is 2e to the 5x over 25 dx, close bracket. Okay, now let's look at this remaining integral right here. So this is a very nice integral, 2 over 25. That's just a constant, right? Coefficient in the front, and all we're doing is integrating this exponential. Right, so that's going to be pretty easy. Let's go ahead and do that. It's equal to x squared e to the 5x over 5 minus 2x e to the 5x over 25 minus, and when we integrate this, it's just e to the 5x with extra 5 on the bottom, right? So that's going to be 2e to the 5x over 125. And then, now that we don't have any more integrals, we can add a plus c. Okay. And that's basically how it's done. Of course, you can work furthermore to clean this up a little bit. I'm going to leave it here since we're running out of space. So this whole thing is your answer right here. Okay. Now, this first example is to show you that sometimes we have to use integration by parts more than once, right? In this case, we used it twice because we started with x squared, and in order to make this integral work, we have to perform integration by parts twice to get rid of this first factor, which is the polynomial, right? So notice that after two times of integration by parts, the remaining integral does not have the algebraic part anymore. It's just the exponential, the e to the 5x left, right? And from this point on, we can just perform simple integration and get to the result we wanted. Okay. Feel free to stop and try to look at all this work. And if you have any question, feel free to come on to my office hour. All right, let's look at the next one. All right, example 2. I'm going to show you a very nice shortcut for integration by parts that only works for these two types of integrals. All right, the first one is when you have a polynomial multiplied by an exponential, just like our example 1. And actually, we're going to use the same example to show you how this shortcut works. And the second type is when you have a polynomial multiplied by a trig function. Right, so the idea is, polynomial, we can take derivatives however many times we want to get them down to a constant, right? And for exponential and trig, doesn't matter if we're doing integration or derivatives, these two types of function will never go away, right? The derivative and integral of an exponential is still an exponential, and the derivative and integral of a trig function is still always a trig function, right? So it only works if you have these two types of integrals. And this method is also called the tabular method for this shortcut. So basically, there are 3 steps. First is we differentiate the polynomial down to 0. Second, integrate the trig or the exponential function the same number of times. Step 3, multiply along the diagonals going down to the right, applying an alternate sign starting with a plus sign. So don't worry, I'm going to walk you guys through this. All right, so let's construct 2 columns, and one column is going to be differentials, and the other column is going to be the integrate. All right, so polynomial and exponential. So we're going to differentiate the polynomial side. So let's put the polynomials here. And the integration side, we have the exponential, which is e to the 5x. Now we're not gonna worry about the dx because this is kind of like a shortcut. We don't have to be that rigorous. All right, so first step, differentiate the polynomial down to 0. All right, so let's just keep differentiating this thing to get to 0. All right, so first derivative 2x, second derivative 2, and third derivative 0. All right, so we took derivative 1, 2, 3 times. Right, so let me make a little note here. All right, so that's 1, 2, 3 times. That means we have to perform step 2, which is integrate the trig or exponential function the same amount of times. So we have to integrate this 3 times as well. All right, so here we go. So integrate it once, e to the 5x over 5. That's 1. Again, e to the 5x over 5x over 25. Again, e to the 5x over 125. All right, now that we have everything we need, just need to follow step 3, multiply along diagonals, going down to the right, applying an alternate sign starting with the positive sign. So we're going to start with this x squared on the left-hand side, and then move down like that. Move down like that, move down like that. All right. And the first one is going to be positive. All right, so that's positive, and then alternate sign negative and positive. All right, so with everything in here, we will have this. So first x squared times this, so we have x squared e to the 5x over 5, and the next is negative, so minus 2 e to the 5x, 2x e to the 5x over 25, and then the last one is plus. Right, so plus 2 e to the 5x over 125, and that's it. And then don't forget your plus c. All right, so this is essentially the same as the result from here, right? If you distribute this minus sign, we get the same thing. All right, so keep in mind that this shortcut only works for these two types when you have a polynomial multiplied by exponential or polynomial multiplied by a trig function. All right, so let's look at example 3. This is a definite integral. We have bounds from 0 to 1. Now go ahead and pause the video and try to evaluate this integral on your own. You can use a shortcut method, right? Because we have a polynomial and a trig function. All right, so following the same steps, we're going to have a differential column and then integration column. Right, so x and then cosine pi x. Right, so x is just going to be 1, 0. So this is a nice one where you just need to take the derivative twice. So integrate twice. First one we have sine pi x over pi, and then again, so that's negative cosine pi x over pi square. Last, we just need to start from the first column, multiply down. Remember your signs, right? So positive, negative. All right. And then we can just go back to our original integral and then write equal to x times that. So that's x sine pi x over pi minus negative cosine pi x over pi square. Right? So we have two negatives. That's going to be a positive. So x sine pi x over pi plus cosine pi x over pi square. Now, remember that this is a definite integral, so we have to evaluate it from 0 to 1. Right? And let's see what we have here. So we have sine pi over pi plus cosine pi over pi square minus plugging 0, so that's 0 plus cosine 0 over pi square. Right, so let's just evaluate those. Let's see, that's a 0. That's 0. Right, so we don't have to worry about it. And let's see what we have left. This is negative 1 over pi square minus cosine 0 is 1. It's 1 over pi square. And that is negative 2 over pi square. And that's your final answer. All right, here we go. Example 4. Another definite integral of consisting of log and radicals, right? Or algebraic in this case, right? So following our order, right? OIATE, first one is log. Now we put log first because there's no easy way for us to integrate any log expression, right? So in most of the cases, we are going to pick log as your u, right? On y, and then the rest, what dv is going to be 1 over radical y dy. Now notice that this is not one of those cases where you can use a shortcut, right? Because even though we don't have a polynomial, we have some sort of radicals, and we have the log, right? There's no exponential or trig function in order for the shortcut to be working. All right, so whenever you see log, most likely that's going to be your u, right? And then du is going to be 1 over y dy, right? And let me actually rewrite this part using exponents. So that's y to the negative 1/2 dy, right? It will be a little easier for us to take the integral. All right, so integrated, v is the integral of that, 1/2 dy, and that's going to be y to the power of 1/2 over 1/2, which is 2 y to the 1/2. All right, so follow your integration by part, starting with uv. All right, so uv, that's 2y to the 1/2 times ln y minus v du, right? So that's 2y to the 1/2 multiplied by 1 over y dy. And we are evaluating from 4 to 9. Also this part as well, 4 to 9. Okay. But we're going to evaluate it at the end. Let's just keep going. All right, so 2 radical y times ln y minus, this is going to be the integral of 2 over y to the 1/2, right? Or you know what? Let me write it as y to the negative 1/2. Right? Now we know what integral of y to the negative 1/2 is down here, right? So keep going. 2 radical y ln y minus, that's going to be 4 y to the 1/2, right? Evaluating this, that's going to have an extra 2 here, right? So that's 4 times y to the power of 1/2, and evaluate this from 4 to 9 and see what we have. So we have 9, put in here, 2 times 3 is 6 ln 9 minus 12 minus, that's 4 ln 4 minus 8. All right, so let's see what we have here. Going up, that's 6 ln 9 minus 4 ln 4 minus 4, right? And that's it. Okay, so whenever you have log in the integral, most likely you will have to perform integration by parts, and the factor with log is going to be your u. All right, so here I have a question for you to try on your own. I'm not going to talk about the answer here, but I want you guys to figure out what is the integral of ln x dx. Now, ln x is a function that we have been working with closely, right? But if you think about all your calculus classes up to this point, we have actually never talked about the integral of ln x. We know the derivative of ln x, which is 1 over x, but we have not talked about the integral of ln x. So go ahead and try this using integration by part, right? And if you get stuck, there are tons of video on YouTube, and just pick your favorite one and check that out. All right, next, let's look at integral of an arctangent. Now, arctangent, we know what the derivative of arctangent is, but we actually don't know what the integral of arctangent is. So, again, let's follow the order LIATE, right? We don't see any log in here, right? So I would have the inverse trig. So let's pick u to be arc10 of 1 over x. And in that case, what is dv going to be, right? So u is this whole thing, right? And what's left, right? The only thing that left here is dx, right? That's fine, right? It's a 1 times dx. It still works. All right, so moving on. Let's see what du is. Now, the derivative of a lot of the inverse trig function can be quite annoying, right? So feel free to check on your notes or your old notes or on any of the website that gives you the derivative of any of the inverse trig. So that's going to be 1 over 1 plus 1 over x quantity square and multiplied by its chain rule, which is going to be negative 1 over x square. Right? So let me clean this up a little bit. It's going to be 1 over 1 plus 1 over x square multiplied by negative 1 over x square. And that's going to be negative 1 over x squared plus 1. Right, is that right? Let's see. Yep. So just you can distribute the x squared into the denominator and then put the negative sign on top. All right, so that's du, and dv is just going to be x. All right. All right, here we go. And uv, x times that, right? Arc 10, 1 over x, minus v du, so that's x times negative 1 over x squared plus 1. Now I'm going to put this negative 1 combining with minus sign here, so give it a plus, right? So x times x squared plus 1, like that. And you know what? I'm going to write it separately. Okay, and what's left is just to integrate this, right? This is a fairly nice integral. X arc 10 1 over x plus x over x squared plus 1. Now remember that this thing is positive because I combined the minus from the integration by parts with the negative sign coming from the du. All right, so how do we integrate this, right? We have denominator, we have one higher power than the numerator. Now, usually if you have one higher power in the denominator, that suggests it's something of log, right? So if you push it down here and then take the chain rule, you get 2x on top. Well, now we're just missing the 2, so that's nice. Here we go. So that's going to be arc x arcs tangent of 1 over x plus you know what, I'm gonna do u sub to make this a little nicer, a little quick work on the side, right? So let u be x squared plus 1, du is going to be 2x, right? 2x dx. Okay, so that's gonna be u over 2, oops, not a bit, it's gonna be du over 2 and u over 2u, something like that, right? So you push the u down, right? And after you clean that up, you get ln of x squared plus 1 over 2 and the plus c. Okay, And that's it, right? You can check your work on that. Check my work on that, right? So if you take the derivative of that, you push it down, right? You get x squared plus 1 in the denominator. And then the chain rule of x squared plus 1 is going to be 2x, right? And then the extra 2 here is going to reduce with the 2 in the denominator, giving you x over x squared plus 1. All right. That's it for this one. All right, our last example of this section is this integral, e to the negative t times sine. Now notice that we have exponential and trig, and they are both non-disappearing, right? Non-diminishing, right? Because no matter how many times you take the derivative or the integral, it's still going to be there, right? So here we come up with a new technique. Again, let's follow LIATE. Right, so let's see which comes first. We have trig, right? Trig is before exponential, right? So we're gonna let u be sine of t and dv be e to the negative t dt. All right, and go ahead and apply the integration by parts by finding du, which is cosine t dt. And then here we have v is negative e to the negative t. All right, let's see what we have. Negative e to the negative t sine t minus v du, right? So I'm combining the minus here. So we have e to the negative t cosine t dt. All right, so here another exponential with trig. So we have to perform integration by parts again, right? So let u be the trig function, cosine t, dv is e to the negative t, du is negative sine t, and v is negative e to the negative t. Forgot dt here. All right, so let's see. That's equal to uv, right? So negative e to the negative t sine t plus negative e to the negative t cosine t minus the integral. So that's two negatives. So we still have a negative here. E to the negative t sine t dt. Okay. Let's see. I want you guys to focus on this integral and the original integral. What's the difference between these two? That's right. There is no difference between these two. Okay. So what does that tell us? All right, let me rewrite the whole thing on the next page. All right. So we started with e to the integral of e to the negative t sine t dt. And then our last part looks like this, right? E to the negative t sine t minus e to the negative t cosine t minus the integral of e to the negative t sine t dt. And then we notice that this integral is the same as that one, right? So what do? If you keep on going with integration by parts, you're just going to repeat yourself, right? So I'm going to take this whole thing, move it to the left, right? So add this integral to the left. So we get 2 times integral of e to the t sine t dt. All right? So what I'm doing is basically adding this integral to both sides. Right? And if you have 2 of the same thing, right, we can just write a 2 in front of it, right? All right. And next, what we have left on the right is just the e to the negative t sine t minus e to the negative t cosine t. And in order to really get this integral, all we need to do is divide by 2. Right? So we get e to the negative t sine t dt is equal to e to the negative t sine t minus e to the negative t cosine t over 2. And this is when you can do the plus c. All right. So in some cases, when you have a product of functions that are non-diminishing, right? For example, here we have exponential and trig, right? This is the technique that you have to use, right? Perform integration by part twice, and when you get back to the same integral, move that integral back to the left-hand side and divide by 2. So we have covered almost all the technique that we need to do, right? So let's do a quick recap. So example 1 is a quick idea on how to perform integration by parts. And example 2, we saw the tabular method, which is a shortcut method. Now, this is actually very useful. You can use this in a lot of different integration by part questions, right? You actually even more than these two. But in order to go straight directly to the answer, it only works for these two types of integral. All right, so another example using tabular method. Right, this is an example where you cannot use a shortcut, but it's a nice practice, right? We see ln and we have a radical, right? Try this one on your own. And one with an arctangent, right? Anything with involving the inverse trig is pretty annoying, right? Especially when you need to take the derivative of inverse trig function. They are quite annoying, right? So, have a no car on the side. All right, and the last our example, right? When you do it twice and then move it back to the left-hand side, divide by 2 to get the answer you want. All right, thank you guys. That'll be all, and definitely come on to my office hour if you have any questions. Have a good day. Bye bye.